Okay, so today we're going to analyze ideal and non-ideal. So I'm just going to give you the equations for ideal gas, which you've kind of seen. Some of you might not have, but they're just equations that govern the right side of the vapor dome. Okay. So it's always good to review these. So temperature, specific volume. There's our nice vapor dome. How many vapor domes? Are you sick of vapor domes yet? Yeah, that's what pretty much this is thermo, is vapor domes, figuring out where you are and then applying the first law of thermo. Your next chapter, you're gonna get sick and tired of writing the first law, but it'll drill it in your head and you'll never forget. Or vapor domes. So what we're going to deal with today are equations for the right side. So in the gas region. And these gases compress or expand differently. And we assume an ideal case. Sometimes they do non-ideal case. That's the bottom line of today's lecture. Okay, and I'll show you how to do both. Okay. So, ideal gas equations. Whoa. And pretty much after this section, you're always going to assume ideal because it makes life a lot easier. Okay. There's many. So P equals rho RT. PV equals MRT. Then we got P little v equals RT. And then PV equals NM RUT. This is the number of moles. And this is a universal constant. Oh. Just give you the number. I'll write all these down and we'll go through. So let's go right from the top. So P equals rho RT, so rho is your density. Then we have PV equals MRT. Then P little v equals RT. And then down here deals with the universal constant and the number of moles. And then down here you can actually figure out what your R would be if you know your universal constant and your molecular weight. Okay. So these are pretty much the fundamental equations that they use for ideal cases. Now, in order to use these equations, what's that? It's open book, open notes all the time. Yep. So these are just some rules that they use to make sure that that the gas expands ideally, and it's the temperature that you're using has to be greater than or pretty close to 2 times your critical point, which are found in the tables, and your pressure needs to be 5 times less than PC, your critical point. All right, and these are found. TC and PC are found on table A-1. All right, it's just saying that it's a high temperature compared to your vapor dome, which these are the critical points at the top, and your pressure just needs to be lower than that. And there's a couple homework problems that just use those equations. All right. So that's pretty straightforward for ideal. For non-ideal, meaning it just expands, not ideally, the way we want. All we do is we add a z in front or to the right side of all those equations. So I just picked PV equals RT in this one, so I put z in. Z is the compressibility factor. So if z equals 1, that means it's ideal. And this z is a function of two other variables, TR and PR. TR is your temperature over TC, and PR is your pressure over PC. Oh, and we might as well give you one more. Just another equation. VR is V PC over R times TC. All right, and these are just the steps. If the problem is saying it's a non-ideal case, this means the gas just expands differently. And we use these setups, okay? We use that along with, and I'll go back there to this chart, the graph, right there. So on the y-axis is your z, your compressibility factor. Your x-axis is PR, okay, which they call reduced pressure. And then on this, there's lines of TR. Okay, so why don't I snapshot this? Okay, there. So if I draw a line like this, oh, didn't quite follow it, but you get the point. That is one value of TR, which is 1.5. Okay, so you kind of have to identify what your PR value is. So say it's 3. So say we're at 3. And our PR value is 1.5, so we're right here. Then what we do is we go left, and we find that Z is 0.8. Okay, so that's how we use this chart to figure out our compressibility factor. Okay.
Where is that chart?
Yes, you have to use this chart.
Where is that?
It's in the back. It's actually in the chapter 3, but also in the there's an appendix value for this. Okay, let me show you that because that one has a little bit more information on it. I got to remember where exactly it is. So it's good question. We'll find it. Right here. So there's two. The top one goes from 0 to 1 for PR, and I believe the bottom one goes from 0 to 7. Okay. But in here, they have Z again, but they've also now, these lines that curve are your TR values. All right. Then you also have these dotted lines, which are your VR values. Okay, so that one's a little bit harder to read because it's smaller. But you could use the other chart, which is right in the chapter 3, to figure out your Z value, and then you can use that to figure out anything you need to. Okay. All right, so let's do a practice problem on that. Make sure you know how to do that. Okay, so we got CO2 at 27 degrees C, and the pressure is 3.8 megapascals. We want to store 3,000 kilograms, and we need to find the volume. Pretty practical problem, right? And actually, you could kind of think of propane, the heat used for the house. How big of tanks? How you need 2 tanks, 1 tank, depending on how much you use for the winter for heat. Okay. Usually, what they do is they find the size and they multiply by 20 to 30%, because what happens to gases as it gets cold and warm? They change sizes, so you want to factor all that in. Yep. Okay. So what do I have here? Let's kind of get right to the solution. We'll skip all that other fun stuff. Whoops. So from Appendix A1, we find that TC is 304 Kelvin and PC is 7390 kilopascals. So, based on the rule, we have 27 degrees C. What is that in Kelvin? At 273, so about 300. Remember that rule that I showed you we could use for ideal? Is 300 greater than 2 times 304? No. So we know we have to use the non-ideal equation, meaning this is not going to expand with a z factor of 1. So let's find TR and PR. This is T over TC, which is 300K over 304K, 0.987. PR is P over PC, 3800 kilopascals over 7390 kilopascals. Did they give you megapascals? Okay, so I just converted that. All right. I'll pause here to make sure you get caught up. So again, we know we can't use z of 1 because it doesn't violate it violates this one of these rules out of the 2. Okay, so we need to find our TR and our PR, which we did, and now we can do what? Use the chart, right? And we can find approximately what z is going to be. So this is pretty close to 1. So let's use a TR of 1 and a PR of 0.5 to get us roughly what it's going to be. So let's go to the chart, and I don't want to use that one because that one's messy. Let's go to this one. So, actually, let me go back here and let me paste it and we'll highlight it. Yeah, I already have it highlighted, so I'll just do it again though. Thank you. Okay. That would work with a highlighter. Try it. PR is what? 0.5? Oh, look at that. That's much better. And then we're at a TR of what? 1? So we're actually, I want to actually draw this so you have it. Take that off. Yeah. So we're on this one. Okay. Now, we can then scroll over across. And what do we get? Yeah, 0.8. Okay. Now it's going to be off by a little bit, but that's fine. Okay. So 0.8. So now we know Z. We can then say PV equals ZRT. We can solve for V. And just to save space, I'll go to the right. Oh, R value is 188.9 joules per kilogram K. And this is found on A-1 for CO2. We got that, we got that. Temperature, 300 K over the pressure, which is 3,800 kilopascals times 1,000 pascals over 1 kilopascal. 0.0115 meters cubed per kilogram. Then what? Now how do we find big V? Yep. So if you notice, this stuff wasn't too bad. This is just enough to store it, right? So you definitely want to go bigger. But it gives you an idea of a baseline of, okay, you can't go any smaller than this. Otherwise you'll have to bleed off some of the mass.